Every time your phone connects to a 5G tower or an advanced radar tracks an aircraft, an invisible piece of technology is working to keep that connection alive. It's called a phase-locked loop, or PLL, and its entire job is to keep high-speed signals locked exactly on target. For years, the gold standard for doing this has been the vectorized square PLL. This architecture takes incoming signal waves and plots them as vectors, tracking them across a standard 2D square grid known as the IQ plane. But this square grid creates a mathematical bottleneck. Because the signal vector is constantly rotating through the empty space between the rigid x and y axes, the system has to pinpoint its exact location by calculating the hypotenuse. The processor is forced to run heavy trigonometric functions like sine, cosine, and arctangent millions of times per second. All of that continuous math forces the processor's arithmetic logic unit to work in overdrive, creating computational drag, excess heat, and system lag. Worse, because the processor uses floating point decimals to measure those angles, it generates tiny rounding errors that stack up into signal jitter, called phase noise. To fix this, hardware engineers are physically abandoning the square grid. By tearing out standard math processors and replacing them with an architecture called the K4 PLL, they map the signal onto a 3D interlocking tetrahedral mesh. By changing the environment's underlying shape, signal processing stops being a heavy mathematical calculation problem and becomes a highly efficient, pure geometric routing problem. This shift starts right at the front door, in the pipeline's ingestion layer. A legacy analog-to-digital converter normally turns an incoming voltage into a standard linear integer. The K4 Quantizer entirely bypasses that. Instead of projecting the wave onto a flat plane, the K4 Quantizer maps the voltage into a discrete 4-part barycentric vector. It forces the incoming analog signal into the tetrahedral grid, snapping it directly to the exact corners of the shape, without ever letting it rest in the empty space in between. Because the data is locked to these exact physical coordinates, the ingestion layer requires 0 floating point registers. It deals strictly in ultra-fast discrete Boolean logic, ones and zeros. This diagram shows the functional units of a standard arithmetic logic unit, specifically the blocks dedicated to addition, subtraction, and complex arithmetic. In the K4's core processing engine, these heavy mathematical hardware components are bypassed. When the processor needs to advance the signal's phase on this rigid tetrahedral mesh, it doesn't need to calculate a new angle. Trigonometry is deleted from the workflow. Instead, the processor uses an adjacency matrix. To move the vector, the system simply looks up the next connected node and shifts the ones and zeros straight down a pre-existing integer edge. By replacing heavy floating-point trigonometry with simple combinatorial routing, the K4 eliminates the vast majority of the thermal and electrical overhead required by traditional ALUs. Even the most efficient systems experience thermal noise, which brings us to the error correction layer. In a legacy PLL, if a signal drifts out of phase, the hardware has to calculate the exact fractional time delay and then slowly ramp up a voltage to help the signal catch back up. That process takes time. Pushing the oscillators slowly back into alignment inherently introduces lag and jitter into the loop. The K4 handles errors using the K-basin operator. If interference causes a vector to drift off its path, the system skips delay calculations. It performs a geometric parity check, physically snapping the signal back to the nearest valid node. Because this correction relies on spatial graph proximity rather than measuring temporal delay, the fix requires no integration. It happens in a single clock cycle. By keeping floating point decimals completely out of the grid, phase slip and jitter are structurally eradicated. A fractional error is physically impossible to route. Once the signal successfully navigates the internal mesh, it reaches its final destination, the output layer. Here, a digital-to-analog converter steps in to hand the data back over to the macroscopic world. The converter takes the discrete, triangulated Boolean route from the processing core and interpolates that rigid path back into a continuous analog waveform. Because the signal experienced 0 decimal rounding errors while moving through the internal logic gates, the resulting analog envelope emerges mathematically pristine. When a digital processing pipeline operates without fractional math, it achieves total phase coherence. This allows the hardware to maintain signal integrity across exceptionally wide frequency ranges, without the cumulative noise that typically limits high-speed data. By changing the geometry of how hardware looks at a signal, trading a square for a tetrahedron, engineers have bypassed the architectural bottlenecks that defined the previous limits of digital transmission.